Hey guys, so this is my video that's going to go over some of the problems from chapter 9. So let's start with this, and we talked about this a little bit when we were in lab. So we want to identify the different blocks. So this that I'm putting the black around right now, this is the S block. So we have that. The P block is right over here. The D block is there. And the F block is down here. So as you go with electron configurations, and we're talking about the different orbitals, or generally these are the subshells, right? These are the locations that you're going to need to identify. Let's go on to question 2. This you've seen in lab, in your pre-labs, and now on here, and we've talked about it really quick. And so this is number 42. You can look at some of the other problems in the book when it comes to things like the electromagnetic spectrum. I talked about that in class a little bit, and I'm not going through it because I don't think really when you look at those, that those are hard problems to kind of understand. If you look at the electromagnetic spectrum, you can tell essentially what order they are in terms of wavelength and energy. So just the smaller the wavelength, the greater the energy when you talk about these. And so we're going to go on here into number 42. And when we talk about these guys, this 2 of the emission wavelengths in the hydrogen emission spectrum are 656 nanometers, the wavelength, right? And 486. And so let's write on here 656 nanometers. And 486 nanometers are the 2 that we're going to look at. One of these is due to the n equals 4 to n equals 2 transition, right? So excited state to 4 going down to 2. And the other is due to the n equals 3 to n equals 2 transition. Which wavelengths corresponds to which transition? And so basically when you guys are looking at this, the thing to remember is the smaller the wavelength, the larger the energy of the photon. So when we're going on here, basically, if you look at these, you're like, okay, which one is smaller? Well, this one is smaller, so it's going to correspond to the greater energy transition. So this one is going to be equivalent to the 4 to n equals 2 because that's 2 different, basically shell transitions for that energy transition or emissions transition. And the other one, if you look, is n equals 3 to n equals 2. That's only 1. So the 656 nanometers is going to be associated with the n equals 3 to n equals 2 transition, where the 486 wavelength is going to be correspond to the n equal 2 to n equal 4 to n equal 2. So the big thing about this is just look at which one of these is smaller, and it's going to go to the larger transition. You don't have to do all the calculations for this. Some of you guys did it on your pre-lab, but it's not required. You would do something like that, and that's the difference between a majors and a non-majors. Something like that you would essentially see more likely in a majors course. And so now we're going on to 50. And let me do this really quick. I forgot to pull this up. So let me go here, periodic table. I'm going to pull our little periodic table up again, because now we're going to start getting into some of these. Actually, let me look at a different one. I like that dynamic one, but I wanted to have one that has, oh no, I don't want, sorry about that, guys. The correct terminology at the top. Let's see what that one looks like. Not big enough. Would it help, right? Maybe I'll just go ahead and use the dynamic one, and I'll just write the individual things at the top that I want you guys to see. Okay. Thank you for being patient. I'm doing this so late at night, right? It's kind of like my brain isn't working all the way. I'm sure you guys understand that and you feel the same way. So this is write the full electron configuration of each. And then what we're going to do is we're going to underline the valence electrons and box the core electrons. So I've kind of moved this around a little bit to get the ones that I want, or to combine several different questions into one, just to let you know. Actually, so when we're talking about this one, this is question number 50 on page 318. And so I have this on the top so that we can look and go through. And remember, this is the S over here. Let me change this to black. Remember, this is the S. These are the P's, and these are the D's. And I'm talking about these general areas right here. And so if we're doing the N, basically what we're going to start with is this guy right here. And so this is an S, and this is an S. So we have here one S, and this is 1, 2. So that's the 1s2, right? And then we go to the next one, and this is what? It's the second row across, and we're still in this S block. So we're going to write 2s, and again, you have 1 and 2 here. So that's going to give you 2 electrons there. And then we go across here, and this is where we start doing our P. And we're on the second row still, so it's 2p, and then we go 1, 2, and we're 3 over. So it's 1s2, 2s2, and then 2p3. So that's the electron configuration there. Now, when we're talking about the core versus the valence, we're talking about basically on the outside, how many can interact. And so if you see, you're looking at the 2s. So these are going to be your valence because they're the highest number out. And this is going to be your core because they're protected by the other ones that are the highest out. So that's how that works. And you can check it because if you look on normal ones, this is 1A, 2A, and then you go across here and this is 3A, 4A, and 5A. And so if you go, you should have 5 of them here, and this is 1, 2, 3, 4, 5. So that's one way you can check it. So that is essentially what we have for nitrogen. Now let me clear this out so that we can essentially answer the one for magnesium. So we start again here in the 1s, right? So we're going to write 1s here, and then we have 1, 2. So that's going to give us 2 electrons. We're going to go to the next side again, and this is 2s, right? Because we're in the second row. Then you have 1, 2. So you do this. Now we're going over to the P. And so we keep going. We haven't seen magnesium yet. So we have 2p, and this is 1, 2, 3, 4, 5, and 6. So that's 6. Now we go to the second one, the next line, right? And you'll notice magnesium is here. So this is the third one. You can see it's always based on those. And so we have 3s, and it's 1 and 2. So that is basically our electron configuration. Now, if you look, this is the 2a, so that'll give you an idea of how many electrons in the valence shell you should have. So that's your valence because it's the highest number out, which is 3. And these are going to be your core electrons that are protected by the valence. So now we're going to go to argon, which is down here. So what's the first one going to be again? If you notice, we start with the same. So we have 1 here. It's going to be 1s, 1, 2. Then we go to the next one, right? That's 2s, 1, 2. We go across. This is the p, right? So it's 2p. And then we go 1, 2, 3, 4, 5, and 6. So that's 6. We go to the next one, which is 3s, because we're in the s there, 1, 2. Then we go across again, and this is 3p. 1, 2, 3, 4, 5, and 6. Again, we look at the highest number. That's going to give us our valence. This is going to be our core, and you can check this again because this is 8a here, and this is 6 plus 2 equals 8. Now, the next one's a little bit different because, let me get out of this and move this down. We're going to go a little bit farther here. So we are in selenium. We're going a little bit farther down. So we're going to start with the same. This is 1s, right? And we write that down, and that's 1, 2. We go to the second row. That's 2s. 1, 2. We go across to that, and that's 2, and this is the p. 1, 2, 3, 4, 5, and 6. We go to the next one, which is 3s. That's 1, 2. We go across, right, and this is the 3p. And this is 1, 2, 3, 4, 5, and 6. Now we go down here. And now we have the 4s, and this is 1 and 2. Now we get here, and we've not seen this one when we've been doing these examples. And if you remember, this is the D. Now the D is always going to be whatever we're looking at. So it's going to be the row minus 1, right? And so essentially here we have 4 minus 1, which equals 3. So it's going to be 3D, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's going to be 10 there, right? And then this is the P. We go back to the regular 4P. And then we go 1, 2, 3, and 4. It's 4. Now, this is where the core and the valence are a little bit different. You again go, the highest numbers here are the valence, right? And you can check this because this should be 6a. So if you look, this 6, 4 plus 2 is 6. So that's right. This and all of these are going to be your core. So this is examples of how you can do the electron configuration, the full electron configuration. Now what we're going to do is we are going to do the shorthand, right? Because if you get down here, do this. If you get down here, you may not always want, even for some of these shorter ones, you may not want to write all of that information, right? So there is a shorthand that you can do, and this is number 54. Did I not do the one? I thought I had. I do. we'll do this. So this is number 54. Wanted to make sure that I got everything in there. And so let's go through here and do it. So let's go look for bromine. Let me make sure I'm in the right area. And so we can see that that is right here. So what you're going to do is you look at this line that is here, and you go to the noble gas that is on the line right before it, which is argon. And what you're going to do is you're going to bracket it and write argon here. And then you're going to start from that, because this is basically saying everything to this point is written the same way. And then we start here, which if you look, we're 1, 2, 3, 4. So we're going to start with the 4, and we are an S here, right? So that's S, and it's 1, 2. So you're going to put 2. Now this is 4, so remember, you're going to do the this row that you have that's going across minus 1. So this is 4. So you're going to do 4 minus 1. So then you're going to get 3. And this is the D, if you remember, right? And you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10. And now we're back into the P. So we go back to 4, right? P. And then you do 1, 2, 3, 4, and 5. So that's how you do shorthand there, right? So let's do the next one. Iodine is right underneath it here. So we're going to start with krypton. And then we're going to go down there. So if you go, we're going to go over here, and we're 5s2. And then it is basically 4d. And you're going all the way across it, right? So that's 10. And then we're going to go back to 5p. And you are 1, 2, 3, 4, 5. So that gets us there. Now what we're going to do is go to, cesium. So this guy right here is here. So you go to right before it, which is xenon. And then you are here. There's only one. So 6s1. So this makes it much easier, so that if you're farther down here, you're not writing all of this that's up here consistently all the way down. So now let's look. Get out of here. And go to number 60. So now what we're going to do is we are going to write the orbital diagrams. And how we do this is essentially we are going to look at this and put them where they need to go. So we're going to start with neon is here, right? So we're going to go and we're going to have and they just start talking about the valence electrons, right? So what we can do is you can start by writing the electron configuration. That would be the easiest thing. So we have 1s2, 2s2, 2p, 2, 3, 4, 5, 6. So these are going to be the valence electrons. So that's what I'm going to write it for, right? So if we do the 2s, there are 2 of them involved. So you're going to have an arrow up and an arrow down because that's full, right? And then here you have basically 3 p orbitals, right? You have the 2px, 2py, and 2pz. You could write these all as just 2p if you wanted to. And so basically you fill them each with an electron. You have 6, so that's 1, 2, 3, because that's Hund's rule for stability. And then you could go back in there and fill them and pair them. So that would be the orbital diagrams for the valence electrons for neon. Let's go down to iodine. So iodine is right here. And I can tell you, let's do the shorthand. We have krypton here, right? And then we're going to go down here to 5. So we 5s2. We have 4d10, and then 5p, 1, 2, 3, 4, and 5. So that helps us kind of get an idea of where we are going to be with iodine, right? And so our valence electrons are here and here. This guy is considered core, right? Because he's D. And so again, we have 2 for the S. So we have 5S, 1 and 2. And then we have the 5P. And so we have 1, 2, 3, 4, 5. And so one of these will be left. So the last one we had 0 unpaired electrons, right? Here we have 1 unpaired. Let's go with the next one up there. So SR, we're going to see right there, right? So what we can do is we can look at the neon gas, Kr, and krypton. And then we go to the next one, which is 5s1. No, right? This is 1, 2. Try to get you there. So it's 2. And so basically you only have that 1. And so this is your only valence, and there's 2. So your 5s would be full. Let me move this up. So the next GE, germanium, is there, right? So we can go and put argon and then start here. 4s2, 3d10, and 4p1, 2, right? So when you do this, this guy, remember, is core. So you're going to have 4s, do 1 and 2 because you have 2 of them here, right? And then you do the 3 for the 4p, and you do 1, 2. So how many unpaired electrons do we have here? Essentially, if you look, you have 2 unpaired. So you look and you just look at the ones that don't have a electron pair with it, right? The last one, all the electrons were paired, so there weren't any there. So that gets us through that guy. Let's see what the next question is. How many valence electrons are in each element? So you can do what we've been doing, or you can do the top. This is number 61. You could do the top and just find them. So this, if you look, generally this one has the numbers on top, but basically this is 1A, 2A, go across 3A, 4A, 5A, 6A, 7A, 8A is generally. So oxygen, if you look, it's here, right? And if you look up there, there's 6, so it's an easy way for you to look. S for sulfur is right underneath it, right? So that's 6. Bromine, down here, you can look, it's 7. And over here, rubidium is here, so it's 1. So you can go through and do the electron configuration to figure these out, or you can do it really quick by using these numbers at the top. Now here, oh, it kind of, sorry, I'm going to have to go through here really quick. So here, let me see, let me take this off really quick. Sorry about this. When I pasted it from the book, it kind of went through. So let me color these out so I'm not confusing you guys with double words on there. And you can just do this. Okay, there. You go to black. So this is number 76 on page 319. And so let's look through. So you can go and you can start here, and then it's 3s1. So you go to 3, this is the S, and this is the first one. So it's sodium. Here, you go to Kr, which is here, right? And then it's 5s2. So you're like 5s2, and I would just check them. 4d10. So that's one all the way till you get to here. So that's cadmium. And I would just suggest that you guys, I'm going over a handful of them, but there are tons of these problems. And if you go through some and you want to make sure that, oops, it did it. Let me get this out. You want to make sure that you have gotten them right, you can always email me a copy of it or text me and I can let you know. So this one, you're down here with Xe, right? Xeon, and then it's 6, so you can look here, and then S2. So at here, it is barium. So it's really easy to do it this way, right? This is backwards from what we were doing earlier, but it's pretty straightforward. So let's do this one. So we have Kr, we're starting here, and then we have 5s2. So it's 1, 2, 4d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5p3, 1, 2, and 3. So we have antimonium. So pretty straightforward, not terrible, right? Going through here. Now, this one right here, number 77, page 319. So you're going to go through here and you are going to basically pick the element that has the higher ionization energy with every pair. So let's do this. The first one is As, which is here. Let me reference you to this table. So this is where you can go, and they have ionization energies on page 310. So what we're doing on here, right? And you can tell ionization energy decreases as you go down. And it increases as you go across. So we have As, and then we have Bi, bismuth, and arsenic. So they're both the same distance here, right? So then you're going to look, so we're not going to regard this one here, we're going to look at this. And that the ionization is lower the higher you are. So we're going to have Bi there. So the next one is here and here. So we're not going to look at this side. We're going to look here, right? So on here, the bigger one is going to be bromine. Next, we're going to look at S, sulfur, and iodine. This one we can't determine based on periodic properties alone, right? Because basically if you look at this one, iodine is farther over, but sulfur is higher. So on this, we can't tell using just periodicity or the table itself. We'd have to look farther into this. And then the last one is S for sulfur and Sb for antimonium. So as you go down, it decreases. So this one is higher here, right? And it's higher this way and up here, right? This way. So sulfur has the highest ionization energy. So this is how you do it. You just look, you figure out as you go down, ionization energy decreases. As you go across, it increases. And basically, when we're looking at this, the trends in ionization energy basically are consistent with the idea of atomic size. So smaller atoms are more difficult to ionize because basically their electrons are held tighter to the center. So as you move across the periodic table, atomic size is going to decrease and ionization energy increases. It's kind of the same as we move down a column, atomic size increases, so ionization energy decreases. And the next thing we're going to look at is we're going to go on this and then we'll talk a little bit more about atomic size here in a second. So as we look, here we are at number 80. And so let's look at the three. We have Ga, we have In, we have F, we have Si, and we have nitrogen. So then I'm going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So if you remember, this gets decreased and this is increased. So we're going to go from smallest, because it says arrange the elements in order of increasing ionization energy, right? And smallest to largest. So whatever is down here, the farthest to this side, right, is going to be the smallest. So we can look and we can see that this guy is there. So we're going to put In, and that's less that as we go. So we can basically go as we're going this way, right? Ionization energy is going to increase basically, right? So then we can go and we're like, okay, we got that. The next one is gallium. So he's going to be there. And then you look, it's going to be silicone. Got that. Then nitrogen. And then fluorine. So yeah, if this helps you, this corner over here, right, It's the farthest over this way, and it's the highest up. So this is going to be the greatest ionization when you're looking. So that's how you arrange them according to size. Hopefully that helps a little. Let's see. Now let's talk about atomic size. So we're at 83 now. So when we're looking at atomic size, you can look at page 308. So let's find them on here first, and I will tell you the size increases going down, and the size decreases going this way. So basically, this is the opposite of ionization energy. Ionization energy was really high up here, right? But the highest that we have here is basically, this is almost like an inverse. This over here is going to be the biggest. And remember what I said is the smaller the essentially atomic sizes, the harder it's going to be for electrons to leave, so the less likely they're going to ionize. It's kind of like, you know, the closer your parents keep you to them, if like you have a really small house, it's going to be really hard to get away from your parents because they're always there and they're going to keep you close. But if you have a really, really big house, it's going to be easier, basically, for them to leave. So I would say the idea of you leaving is like ionization energy, and how big your house is and how much your parents can keep their eye on you is the atomic size, or how big your house is. Hopefully that helps a little bit. So let's look and find these. Okay, let's start with calcium is here, right? Rubidium is here. Sulfur is here. Silicon is here. Germanium is here. And fluorine is here. So basically, which one's going to be the smallest? Well, it's going to be smallest is over here, right? So here, it's the exact opposite. Fluorine is going to be much smaller, so we got that. Then the next one we can look at is sulfur. So that is there. And then we can go here, and the silicone is the next biggest. And then we go to uranium, which is here. And then we are going to go all the way over here, and then we're at calcium. And then the last one is rubidium. So basically, the atomic size is the opposite of the ionization energy. And I believe is this our last question? Yes, this is our last question. And so on metallic characters, this is number 87. And you can find this figure on 311, right? So metallic characters decrease as you go down and decreases as you go across. So the least metallic is going to be over here. So basically, let's look here. We have FR. Look, SB. Here is SB. IN is here. here. BA is over here. And francium is over there. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let me make sure I have metal characters decrease. I actually wrote this wrong. I'm sorry, guys. Metal characters increase over here. So it becomes more metallic as you get here and less here. So the most metallic you're going to have is actually here. So this is going to align up basically kind of closer with atomic size. So our biggest that we're going to get I'm looking. The metallic size increases, decreases over here. So it's the smallest. So we're going increasing. So we're going to start with smallest and go to largest. So the sulfur is the smallest. And then, wait, do I have it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No, 6. Oh, okay. Selenium is there. And then we have here antimonium. So we're going from smallest to largest. We have Iodine there. Then we're going to go all the way across to barium. And then the largest we have is francium. So this does line up basically with what atomic size looks like. And so that is just a review of some of the common problem types that you can see. I would essentially look over your over the general concepts ideas that we talked about, and looking over kind of energy and wavelength and those kind of things on top of the problems that we just did here. Thanks, guys.